In this last part of 4.3, our objective is to use the properties of definite integrals. The reason we want to be able to use the properties is it can be shortcuts. It can make it easier to evaluate definite integrals. Let's remember one really important thing as we work through these properties and use these properties. Definite integrals means net area. When it says find the definite integral, we're finding the net area. So keep thinking in terms of area. If a function is defined at x equals a and the limits of integration are both a, that means we're not going anywhere. It's not from a number to another number that we're creating area. It's from a not going anywhere to a. So are we creating any area? No. So it will equal 0 when the limits of integration are the same. No area is created. If we reverse the limits, notice normally we're saying from a to b, low to high number. Well, sometimes the definite integral just happens to be written such that it's high to low number. So integral on a to b, usually we say low number to high number, but if it's backwards, we need to switch it so that it makes sense, so that we're talking about area from a low number to a high number. If we switch it, notice b to a gets switched a to b. If we switch it, it becomes negative. Why does that happen? Well, think about when we have first defined the definite integral. The definite integral has in it the limit of the sum of the areas of the rectangles. So the limit of the sum of delta x times f of x. Well, remember delta x is b minus a over n. If those are backwards, if it's a minus b over n, how are those related to each other? Well, a minus b is the opposite of b minus a. Those are the negative of each other. So we switch the symbols and we get negative. Third property, f is integrable and determined by a, b, and c on closed intervals. Then what does this mean? The definite integral from a to b equals these two integrals added up, a to c plus c to b. Why is that the case? Let's look at the picture. The interval on a to b. This is going to be the widest interval since it'll make more sense with c being between. So we'll say put c about here, and let's draw the function just like that. So the integral, definite integral from a to b, because I made it just a positive function, it'll be easier to see. It's all of this area in there. It's that shaded region. Let's make these axes darker so it looks different than our shaded region. Okay, so that's the area, the definite integral from a to b. The area, the definite integral on a to c, well, that's going to be this region right here. And the definite integral on c to b, well, c to b, that's going to be this region right here. So this is saying put these two areas together and you get the larger area. Makes sense? It should, and it will be useful. Another property, remember that the definite integral comes from the summation, and remember the summation properties. So if you have a constant times f of x, that constant can be removed to the outside, can be pulled out, just like we do with summation, with sigmas. Another property that we use with sigmas is when we have sum or difference, we can split it up. Well, we can do that with definite integrals as well. We can split it up because it comes from the sigma. Let's take a look at some examples that use these properties and see why they will be useful. Evaluating these integrals. So from an AP exam, what are all the values of k for which negative 3 to k, integral from negative 3 to k of x squared dx equals 0? Well, if it's going to equal 0, remember that these limits could be the same thing. Another time it equals 0 is when there's an odd function and we're going equidistance, but is this an odd function? No. So having the limits be the same will create a net area of 0. Second example is a good example of how useful the properties can be. So splitting this up into the definite integral from negative 5 to 5 of negative x cubed over 2 dx plus the integral from negative 5 to 5 of 4 dx. Because this is an odd function, see the x cubed right there, and my limits are equidistant from the origin, this definite integral is just 0, and I don't have to do anything for that. So that's really just gone. This one, well, let's think of this graphically like we did in the few examples in the previous video. If we were to graph the function y equals 4, f of x equals 4, that is just a horizontal line that crosses through the y-axis at negative 4. If I'm graphing it on the interval from negative 5 to 5, that's this area that's right here. What type of shape is that? That's right, that's a rectangle. What's the area of a rectangle? Its width times its height, or its length times its height. How long is it? 10 units. How high is it? 4 units. So what is 10 times 4? 40. So splitting this up, we have this area of 0 plus this net area of 40, and without having to do too much work using our properties, we're done with that one. In number 3, also multiple problems taken from AP exams, we're given information about the integral of a function on 1 to 10 is 4, and from 10 to 3 is 7. Let's use our properties. So pull out the 3, and we're doing 3 times the integral from 1 to 10 of f of x. And knowing this one, well, that's just a substitution. This comes out, 4 goes in its place, and we get 3 times 4, or 12. The next one, well, look at what we have here. No area is created. I don't even have to look at what the function is. Looking here, the integral from 1 to 3, well, I don't have any integrals from 1 to 3 up here, but I have 1 to 10, and I have 10 to 3. So remember splitting it up. If we think about 1, 3, and 10, we have the integral from 1 to 10. All this much is 4 of net area. 10 to 3 is backwards. So let's switch that around to the integral from 3 to 10. And remember, when we switch it, it becomes the negative of what it was when we switch the limits. So from 3 to 10, that's negative 7 of a net area. So we can think of taking that entire net area of 4, subtracting the part that we don't want to be left with the part that we do want, that integral from 1 to 3. So minus negative 7, and 11 is our final answer. One last example, again from an AP exam. If the integral from a to b of f of x is a plus 2b, what's the integral from a to b of f of x plus 5? Well, again, let's use our properties, splitting up the integral first. And the reason we want to do that is because we know this one. We were given it as a plus 2b. So a plus 2b can go in the place of that. Then we've got this. Well, again, look back to how we did number 2, where we thought of it graphically. And graphically, 5, y equals 5, the horizontal line, looking on A to B, the area of a rectangle is what we're going to find. So what's the width or the length of that rectangle? B minus A. What's the height of that rectangle? It's 5. So multiply the length times the width, 5 times B minus A, and that's what this definite integral is. Let's put them together. A plus 2b plus 5b minus 5a. Simplify a little bit, combine our b's, that's 7b, combine our a's, minus 4a. That's the best we can do given that we don't know the values of a and b.